Okay, so Unit 7 was all about scale factor and similarity, so we were really thinking about scaling things up for enlargement or down for reductions. We started with unit conversions, just to be able to go from like inappropriate units. For example, the height of this classroom is 2,930 millimeters. Hey guys, thank you. It's really hard to visualize a measurement like that. Or the length of an iPhone is a fraction of a meter. That's a weird way to think about it. So converting to more appropriate units will be part of the test. And so we're able to use this to help us do that. And so this is showing that the entire metric system is balanced around the meter, and every step in either direction that we're taking is either dividing by 10 or multiplying by 10. So it's really nice because all that is moving the decimal place from where it is, either moving it left or right, depending on if we're multiplying or dividing. So if we have the height of the classroom being in millimeters, what would be an actual appropriate way to measure the height of this classroom? Meters, for sure. So we want to think, okay, what would this be in meters? And so if we're going from millimeters to meters, that means we're going to take 3 steps to the right, where every step to the right is dividing by 10, which means we're really thinking that the decimal place starts at the end of the number. And for every step that we're dividing, we're moving that decimal place 3 steps to the left. So it ends up bringing us with the decimal place now right here between the 2 and the 9 instead of at the end of the number. So what we end up getting is 2.93. The 0 isn't really necessary anymore. So 2.93 meters, which feels like a more appropriate way to measure the height of a room. You can picture, okay, that would be just about 3 meter sticks stacked on top of each other. Okay, cool. For the next one, the length of an iPhone is 0.53 meters. So we're thinking the length, which is the longest distance here. What would be a better unit for that? Centimeters would be a good choice. So to go from meters to centimeters, we're going to the left this time because we're going from a bigger unit to a smaller unit. So for every step, we're multiplying by 10, which means we're making the number bigger. And so this will move our decimal place 2 steps to the right this time, which means that we'll get 15.3 centimeters. And that's something you could more visually estimate. We know a ruler is about 30 centimeters, so about half of a ruler is the length of an iPhone. I don't know if that's fully accurate, but we're gonna go with it. It seems a little bit long, but whatever. And the last one here, the distance from Belmont to Quality Foods is 140,000 centimeters. What would be a better way of measuring that? Kilometers, for sure. And so from centimeters to kilometers, this time it's 1, 2, 3, 4, 5 steps. So we're taking our decimal from being at the end and we're dividing for every one of those steps. We're actually making the number smaller. So the decimal will move 5 spaces this way and we end up getting 1.4 kilometers. For some questions, just like we had on the quiz, there's kind of multiple appropriate ways to measure it in different units. So on the quiz, we had the height of the mountain, and based on the numbers we had, it made sense to either be in meters or kilometers. If that's the case on the test tomorrow, I'll accept either way, as long as it's accurate. So if you are going, for example, let's say it was centimeters to meters, make sure that your number is reflecting only a 2-step change, whereas if you're going to kilometers, it should show a bigger change. So make sure that your number just reflects what the units are with it. Cool. Next up, we talked about scale factor. And so scale factor we think of first as just a fraction in the form our new measurement compared to our old measurement. Usually we're thinking the length of something because this unit's pretty focused on just like the lengths of stuff. So I guess we could say our new length over the old length. When we later get into scale diagram stuff, we end up really thinking of this as being more so like the blueprint. Oh, sorry, we don't usually say old, we say original. My bad. It's kind of the same thing, but it makes more sense to think original. When we're doing this with a scale diagram, we're thinking blueprint versus real life. And just by looking at the number that we get for our scale factor, we can see if it's been an enlargement, a reduction, or no change at all. That usually doesn't happen, but an enlargement will mean that the number is bigger than 1. A reduction will mean that the number is less than 1. It'll still always be positive, so it is bigger than 0. I'm just going to put this for simplicity. And if there's no change at all, then the scale factor will be exactly 1, which we don't see very often, but good to know. We also sometimes will have it written as a ratio. And so a ratio just means that it's got the 2 dots in the middle. And so in that case, we're just taking the top of the fraction and putting it first. So we end up having new as our first thing, and then original second. And we'll see that for examples like these little box drawings here at the bottom when we're thinking about enlargements or reductions. Okay, otherwise we can start with a question here. When it comes to creating a scale factor, we need to make sure that the units match. I'm just going to write that here. And so here we have the height of the Eiffel Tower is 330 meters. That's the original real-life basic Eiffel Tower. And a Lego model is a really good example of a scale factor because Lego actually tries really hard to make it a pretty good reduction to show good accuracy. And so the height of the Lego model is 149 centimeters. So our first step is we need the units to match. So we can either convert this to centimeters or we could convert this to meters. It doesn't really matter. You just have to make a choice. I typically go to the smaller unit. I don't know why. It just feels better to me. So I would say that instead of 330 meters, I would think of this as 33,000 centimeters. So going from meters to centimeters is multiplying by 10 for 2 steps. So really just adding 2 zeros at the end of the number. And so now that we have matching units, we're thinking for our scale factor that it will be new on the top, original on the bottom. Our new is going to be the 149 centimeters. That's the Lego model. Our original is the real life Eiffel Tower. And this is where we pull out our calculator because I'm not doing that in my head. And what you notice is you've got a number with some zeros and then a lot of other digits. And so what I would love for you to do is to always keep 3 significant digits when it comes to the scale factor. So we keep the zeros, all of them, no matter how many there are. And then your calculator will say 451, 51, 51, 51, forever. Technically that is repeating, so we could do that a different way, but I'm just going to keep 4, 5, and then it will round to 2. Because technically it was 4, 5, 1, 5, 1. So we're rounding this up because the 5 tells us to. And so that is our scale factor. And when we're writing a scale factor, it's always nice to double check that this makes sense. And so because this is a number less than 1, we're thinking that this should be a reduction. And the Lego model is a reduction of the real life one. And it's a pretty big reduction. Like the Lego model is way smaller than the real one. So we do expect to have a lot of zeros in here to show that it's gotten really quite small. Just like when we did the version of the Earth one, that was a tiny scale factor because the Earth is massive and it's just a little Lego guy. The other thing is when you're writing a scale factor, the decimal here, there are no units attached. I noticed this on the quiz. So even though we had fixed these as being both centimeters, essentially going into the scale factor, we have centimeters on the top and bottom, and they cancel each other out. And so the scale factor itself is just saying how much bigger or smaller it is. We have no units for this one. Okay. Next up, we've got these box drawings. And so it's good to look at our our ratio that we have and consider it as a fraction. I like to do that to say, okay, instead of 2 to 1, we can switch this over to say 2 over 1. The reason why this is helpful is what is 2 divided by 1? 2. And since, again, that is larger than 1, that means that we're looking at an enlargement for this one. So we're expecting whatever this shape is to get bigger by a factor of 2. Another way to think about it is, again, that the first number represents our new shape and the second number represents our original shape. So what we're saying is for every 1 box on our original shape, it'll become 2 boxes on the new shape. So going through and just kind of starting with that little dot there. we can say, okay, this was just 1 on the original, so it'll become 2 on the new one. So we go out 2. And we're just following the same direction. So we go down 1, so that means we'll go down 2. Here we're going down diagonally by 1, so we'll go down diagonally by 2. Then we go up 1, and then we go over. Here we see that we're going down 2. And so for every length here, we can also think about it as just multiplying it by this number. So since this was 2, we'll multiply it by our scale factor, and that'll become 4 over here. Then we have a length of 3, so that'll become 6 on our new one. And then closing up our shape, we have this here. And just double checking that it makes sense. This was 3, which means this should be 6, and it is. On the next one, this one's a little bit weird because we don't have any 1s involved. So our scale factor is kind of interesting, but again, we can think about this as a fraction, which would be 2 over 3. And what is 2 over 3 as a decimal? What we get is 0.6 repeating. And so where this is helpful for us is, should our thing be an reduction or an enlargement of our original shape? Reduction, because it's smaller than 1. So we're expecting, also because we don't have enough space here for it to be an enlargement, but we're expecting it to get smaller. And the factor in which it gets smaller is every 3 boxes on the original will become 2 boxes on the new one. And so here I really like to think about it as like chunks of 3. So here we have a chunk of 3 and another chunk of 3, and those will turn into chunks of 2. So we have 2 chunks of 2 on our new one. Another way you could do it is take the entire length you have here and multiply it by the scale factor. And if you did that, this 6 here, when you multiply it by 0.6 repeating, you end up getting 4 as your answer. And so we have a height of 4. Going up diagonally 3 will turn into going up diagonally 2. Going down 3 will become going down 2. And then we go over 2, and we close up our shape. So just like with similar triangles, our shape should have the same structure. It should also be in the same orientation, just based on how we're doing this. That's the easiest way. It should just either be bigger or smaller. Any questions from the front side of the page? Cool. Flipping it over, this is where we get to actually use scale factor to do some stuff for us. It's great that we can figure out the scale factor, but it's nice when it can help us do math. And really what we're thinking is, if you know the scale factor between 2 objects, you can use it to solve for some unknown lengths. And so you want to start with the corresponding side that you actually know, whether it's on the scaled down version or up, or the original version, and then you want to choose to either multiply or divide. Typically, I like to think of this just with the numbers in front of me, which one would make most sense for what I'm aiming for. But what it really is a pattern where if you're finding the new length, every single time, what you're doing is multiplying by the scale factor. So to find the new one, you multiply. So you'll take your original length and you'll times it by your scale factor. Whereas to find the original length, we have to go backwards, and so we need to divide. And I will also just point out, I noticed on the quiz, some people had this backwards. They knew they had to divide, but they started with their scale factor, and then they divided by the new length, which is fine if you switch it up when you're multiplying, because multiplying goes both ways, but dividing, it's important the order that it goes in. So every single time you're starting with like the thing you already know, and then you're multiplying or dividing by the scale factor as the second part. So that's really important. So here we've got Sammy designing a miniature backyard based on her real backyard. She's chosen her scale for this project to be 1 to 25. I would recommend anytime you're given something like this is we turn it into our fraction first. And from our fraction, we turn it into our decimal. So 1 to 25, I didn't leave you a whole lot of space here, sorry. Maybe I'll put it up here. That would be 1 over 25. Yeah, which we end up getting 0.04. Again, if this was a decimal that went on for a lot longer, we would want to keep 3 significant digits just to be able to have some accuracy with our scale. But this will be our scale factor that we'll use to find our new measurements. So if her garden is 3 meters long in real life, how long should the garden be in her mini backyard? And so what we want to think is, because we're finding her new value, her scaled down new one, the new one means we have to multiply. So we will take her original backyard size, which is 3 meters. We will multiply it by the scale factor, 0.04. And we'll see what we get. As our answer coming out of this, we get 0.12. And this is good, but we need to know our units. And so what would our units be for this answer? Meters, because that's what we put in. And so if you were creating a little crafty miniature backyard, would meters be the best way to measure it? No, what would be better? Centimeters. And so to go from meters to centimeters, we're multiplying by 10 twice. So we're moving that decimal place to the end here. So we end up just getting 12 centimeters, which is a lot easier to visualize the little garden in her little backyard. Okay. Alternatively, if we knew the size of something in her mini backyard, we could use it to figure out the size of it in real life, assuming that she had this perfect scale, which is tricky. But this time, if we're trying to find the original length, so it says a tree in the mini backyard is 5.7 centimeters, how tall would it be in real life? We need to divide by the scale factor. And again, I typically like to think, okay, if the tree is 5.7 centimeters, in her mini backyard, do we want it to be bigger or smaller in real life? We want it to be bigger. And so since our scale factor is a decimal much smaller than 1, in order to get this number to be bigger, multiplying isn't going to work, because multiplying by a decimal like that makes something smaller. So we need to divide to make it bigger. We'll get our number and we'll see what happens for our units. This will tell us that it's 142.5. And again, because we put centimeters into our equation, we're getting centimeters out of our equation. But if you're picturing, oh, this is a very small tree. Whoops. If you're picturing a tree in real life, we would probably want to measure it in meters. And so in order to do that, we will divide by 10 twice, which will move the decimal place right here. Okay, our last little bit here on our study guide is all about similar triangles. In grade 10, you have a whole unit all about trigonometry, which is the mathematical study of triangles. It gets more intense than this, but we start with just seeing, are they similar? So the question here is basically, for every side on our big triangle, how does it relate to every side on the small one? And we're calculating the scale factor. We need to make sure that we're choosing the corresponding side lengths, which means we want to choose like the long side on this triangle to go with the long side on this triangle. Same with like the shortest side on this one will correspond with the shortest side on this one. And then we have the side that's left over, and those ones need to match as well. So doing this, we need to check that every scale factor fraction gives us the same one, or the same scale factor decimal. And I typically recommend putting your big triangle numbers over your small triangle numbers. This will just give you a scale factor that's bigger than 1, and it's kind of nicer to look at. That's up to you though. So choosing my big sides, or the longest sides here, comparing those, we get 28.6 over 13. Typing that into our calculator to see what this is, it's 2.2. Okay. Comparing the smallest sides on the two triangles, that's what I have listed here in green. So we're thinking the big one will go on the top, just like we did here, and the small one will go on the bottom. So we'll have 17 over 8.5. Again, typing that into our calculator. And what we get, what did you guys get? Excellent. That's what I got too. We get 2. In this case, I would recommend probably just doing the third one just to, I don't know, see what happens. But technically at this point, we already know that the two sides that we've checked don't have this same scale factor. So right away, we can actually say these triangles are not similar. Usually this question will be led into saying like, are these similar? Show your work to find out. But I do also want you to actually answer the question. Just answering the question isn't enough, but I need to see what your scale factors actually are. But I need you to say something along the lines of yes or no. Yeah.
Do you have to do all three sides if you just get
No, if we see that the two numbers right away are different, we don't have to do the third side. If you're going for a statement that says that they are similar, then you need to check all three sides. Yeah. Okay, our last little bit here is the same idea to what we were doing with the miniature garden in our question above, is we can use the scale factor with these triangles here to figure out an unknown length. And so our first step for something like this is we need to figure out what the scale factor is. We haven't been given that. We've also been given this kind of ominous description of the triangles saying that they're similar. And using this, the order of the letters are really important. This will tell us which sides are actually similar. You might be able to figure it out just by looking at the triangle, like this one probably matches with this one, but for the other sides, it's a bit weirder. And so the order of the letters tells us that the first two, A, B, will be similar to the first two of the second triangle, which are X, Y. And so looking at those pieces on our actual triangles, that would be AB is right here and XY is right here. If you have multiple colors, this is the test to use them on. I say that almost every time though. It also means that the second two letters will match with the second two letters over here. So we're thinking BC will match with YZ. And so just trying to find those on here. YZ is the piece connecting the corners Y and Z. BC is right here. And the last two are also corresponding just by default. And so in order to find our scale factor, we need to choose the right two sides to create this. Again, I would recommend putting big over small just to make your scale factor. But we need to choose the right two sides where we know what they both are and they match in terms of corresponding. So here, this side wouldn't be very helpful to make our scale factor because we don't know anything about this. The yellow sides are super not helpful because we know nothing about anything. But what we do know is the length of this one being 20 and the length of this one being 38. So because we know both those things, we can make our scale factor fraction, 38 over 20. And what we get is a scale factor of 1.9. So we're saying that technically this big triangle is 1.9 times bigger than the small one. And so then we have to see what the question was actually asking us. It said to find the length of BC. So we want to figure out what this is, which means to get started, we're either going to multiply or divide by our scale factor, but we need to pick the side that corresponds with this and for which we actually know something about. So we know that this one here is 13. So we're going to start with that number. And then because the 13 is part of the smaller triangle, if we're trying to figure out its buddy on the big triangle, should I multiply or divide by our scale factor? We should multiply because that's the way that we make the number bigger if our scale factor is bigger than 1. So we'll go multiply by 1.9. Actually, instead of a question mark, I'm going to put the actual BC right here. British Columbia. And so what we get is 13 times 1.9 is 24.7. And did we have any units on this triangle? No, in which case don't worry about it. We don't need a units as part of our final answer. We're just done. There we go. You'll see at the bottom here, I do have a little addition of what's not on the study guide is applying this information with triangle word problems. And also the scale diagrams. So this was not yesterday, but the day before, where you have like a room. And the way that it'll be is instead of measuring stuff on the test, it'll be one of those grid things where we're told that like every 2 boxes is equal to 1 meter. And we need to use that information to find some stuff. So there will be examples of both of these things in the practice test today. And I would recommend maybe just making sure that you get through those questions before you leave today. So if you have questions about them, you can let me know. But otherwise, that was a good little recap of Unit 7.